Sample exam 5. Write the equation in its equivalent exponential form. So we look at and consider the definition. The definition, you want to remember this, the definition says that when I have the log base b of x equal to y, this is if and only if the base, which is b raised to the y, is equal to x. If it's in, we call this the so-called log form. If it's in log form, we can convert to here exponential form. And vice versa. If it's in exponential form, we can convert to log form. So this is like y, the 5 is b, and this is x. And so you take that based on the definition. So we have the base, which is 5 raised here to the y, which is 2. 5 raised to the 2 is equal to that x, which is 25. And it should make sense because 5 squared is indeed 25. This is an exponential form. We take the definition again. Here, 9 is b, right? This is y, and this is x. So we have log base b of x is equal to y. This is if and only if the base raised to the y is equal to x. And so you put that in that form. You put it in log form. So that's log of base 9 of 81 is equal to 2. Evaluate this without using a calculator. Just let this equal to y and use the definition. So log base b of x equal to y if and only if the base raised to the y is equal to x. Well, here the base is 2 raised to the y is equal to 64. We're solving for y. Now notice that 64 is 8 times 8, and 8 is 2 to the third, and that's times another 2 to the third, so we get 2 to the sixth. So if I have the bases are the same, what are the bases? The bases are the same, then the exponents you set equal. So this implies that y is equal to 6. You get the answer. Okay, same thing. Set this equal to y. So this is if and only if 4 raised to the y is equal to the square root of 4. But the square root of 4 is 4 to the 1/2. And so you get y is equal to 1/2. This is by definition is equal to 1. Why is that? Let's set it equal to y, use the definition. So we have 4 raised to the y is equal to 4. 4 is always automatically raised to the first power, so that implies that y is equal to 1. What's the domain? The domain is based on this term here. Oh boy, why did it do that? This term, if you look at the definition, that term there must be greater than 0. So that's not right. by definition, x plus 3 must be greater than 0. That implies that x is greater than negative 3. That is, we have from negative 3 to positive infinity for our domain. Evaluate this without using a calculator. It's an exponential form. I set this equal to y. Still use my definition. Definition says that log base b of x is equal to y if and only if the base b raised to the y is equal to x. If it's in this form, then I can get it back into log form, right? So you pick out what you have here. The 10 is b, right? This right here. And if you don't mind, we may need to change these terms because we've got redundancy with y and y. It's not the same y. We call this something else. Let's call this z, if you will. And so, well, I think that would work out. I think that'll be fine. Yeah, it won't be confusing. So here that y is the same as y over there. And then this term here, well, I guess it is off. Because this is 10 raised to the y, but that's y there. But I better call that z. Yeah, we probably better do that. And so let's see if that makes sense. So here the base is b, and then this is looking over here. So this is y, and then that z is x. So if I write that base, put that in log form now, right, I have the log of base b, that's the 10, of the x, which is z, is equal to y. That y is log of 14. Now, if there's no base, that means it's the common log. That means it's 10. So I have log base 10 of z is equal to log base 10 of 14. Everything being consistent and everything equal implies, that's a 10 and not a w, implies that z is equal to 14. And you were solving for z. Come on, highlighter, don't fail me now. Okay. Again, all I've done so far is just to use the definition. If you remember this is one of those basic properties, but if you forget, again, use the definition. So let's set this equal to y. Now, what is natural log? Natural log, that is to say, this is the log of base e of 1. That's it to be equal to y. If and only if, by definition, this is e to the y is equal to 1. So how to make something raised to a power equal to 1, the power has to be 0. This implies that y is equal to 0. Thus, e to the 0, anything to the 0 is equal to 1. Right? And once you get that, you got to get it. Once you get it, then every time you see the natural log of 1, you know that that's equal to 0. All right. Now, e and natural log are inverses of each other. So what you end up with, and it's a property, that's just equal to 144. Now, let's say if you forget that, and that's fine. That's a J. See. If you forget the property, always use the definition. So this is e raised to the natural log of 144. We set that equal to y. All right, by definition, I'm just going to go right directly to it. So this is log base e of y is equal to the natural log of 144. Again, here the natural log is the base log of base e. That is to say, this is log base e of y is equal to log base e of 144. If all things are said to be equal, y is equal to 144. You see that? Because e is e, log is log, right? And y is 144. So you know, I forgot the property. What is the property? The property says that e to the natural log of x is equal to x, and the natural log of e is equal to 1. So we get the inverses, right? Pretty cool stuff. Also, free, the natural log of e to the x is equal to x. You can bring the x down, so you have x times the natural log of e. Natural log of e is 1, so you get x times 1. All right, we're going to use the definition. If and only if, the same statement here. The left is equivalent to the right is equivalent to the left. This is the base raised to that y is equal to, here x is being represented by x minus 2. So here we have 8 is equal to x minus 2. Add 2 on both sides, we get 10 is equal to x. All right. Use the property of expansion. This is the log base 12 of, of 12 plus, you know, it's times, so it becomes the plus of the logs, log base 12 of x. The property, you remember you have a property that the log base b of b is equal to 1. So this is just 1 plus log base 12 of x. All right. This is another expansion. So this is the natural log of e to the second minus the natural log of 19. And you can write the power as the multiplier. And you remember the natural log of e, well, that's just 1. So we have 2 times 1 minus the natural log of 19. So you get just 2 minus the natural log of 19. Here we do the condensing. So minus means division, right? So that's directly. So, all right. 3 things is going on. The multiplier becomes the power. Do that first. So this is the natural log of x to the third plus the natural log of y to the fifth minus the natural log of z to the sixth. Now, if it's plus, it becomes multiplication, and if it's minus, right, it becomes division, and so you get the answer. The natural log of x to the third times y to the fifth all over z to the sixth. The same old same. So here, multiply the 1/2 through, and so that becomes 1/2 log base 8 of x plus 1/2. I did say multiply. Log base 8 of y minus that power just becomes the, well, the multiplier becomes the power. This is x plus 7 raised to the second. So we're going to make the 1/2 the powers. So this is log base 8. Now 1/2, once it becomes a power of 1/2, that's just the square root. plus log base 8 of y to the 1/2 minus log base 8 of x plus 7 to be squared. Now the next move is you get the answer, right? So you have log base 8 of the square root of xy, and this is minus log base 8 of x plus 7 to be squared, and then that minus becomes the division for the logs, and so you get the answer. All right. We got to find a common base. So take that 4,096 and just divide it by 8 and see what you get, and then see if you can keep on dividing by 8. And what you end up with, you notice that this is 64 times 64. Well, 64 is 8 times 8, so this is 8 to the 4th. So we have the bases the same. That means the exponents I can set to be equal. So we get 2x here is equal to 12. X is equal to 6. The same. This is 5 to the 3rd. So we get 2x minus 3 is equal to 3. 2x is equal to 6. X is equal to 3. Now that 1/4 is 4 to the negative 1, but this is 2 to the 2nd raised to the negative 1. If you have a power raised to a power, you multiply the powers. So now the bases are the same. Bases are loaded, so we set the exponents to be equal. And see how everything just becomes redundant? So we have 5 minus x is equal to negative 2. Let's add x on both sides, add 2 on both sides. 7 is equal to x. All right. Same old, same old. Now this 125 is 5 to the 3rd, and that's raised to the x. And that's equal to, this is 5 to the negative 1/2, right? So I have 3 times x. This implies that 3 times x is equal to negative 1/2. And so x is equal to negative 1/6. All right. When it's in exponential form, just take the natural log of both sides. Natural log of 3 raised to the x is equal to the natural log of 37. So this implies that this is x times the natural log of 3 is equal to the natural log of 37. Divide both sides by the natural log of 3, and you get the answer, the natural log of 37, all over the natural log of 3. Then on your calculator, you find the answer. You divide natural log of 37 by the natural log of 3. All right, we solved this one. And so, again, use the definition. This is 3 to the 2nd equal to x plus 4. So I have by definition, this is 3 to the 2nd is equal to x plus 4. So this is 9 is equal to x plus 4. Subtract 4 on both sides. So we get 5 is equal to x. You check that, you plug in just to make sure that 5 is in the domain. Log base 3 of 5 plus 4. The result is positive. That's all we need. And it does make sense once you finish checking. Log base 3, this is 9, and this is log base 3, and this is 3 to the 2nd. So that gives us 2 times log base 3 of 3. Well, log base 3 of 3 is 1, so this is 2 times 1. We get 2. So it makes sense. All right, we're going to solve this. Now, just look at what we have. This is the natural log of x plus 8 to the 1/2 power is equal to 1. We can take the power and make it the multiplier. Multiply 2 on both sides, so we get the natural log of x plus 8 is equal to 2. Exponentiate both sides. It's natural log, we do the inverse. So we have e to the natural log of x plus 8 is equal to e to the second. Well, the left side, since e and natural log are inverse, all I have left is the identity term, which is the x plus 8. That's equal to e to the second. So we get x is equal to negative 8 plus e to the second, right? Or you can write it like that. Either way is fine. And then on your calculator, you calculate that. That's what you get. So here we solve. Notice that it's plus, so we get the multiplier. This is log base 3 of x plus 7 times x plus 5 is equal to 1. And by definition, this is 3 to the 1 is equal to x plus 7 times x plus 5. So I have 3, just write it, put the stuff on the right on the left side and the stuff on the left on the right side. We like to have x's on the left side. Now you just FOIL that out. We get x squared plus 12x plus 35 is equal to 3. What a funny looking 3. X squared plus 12x plus subtract 3 on both sides. It gives us 32. That's equal to 0. All right, what needs to be there? Because that's important. That's important. So this is x plus, need to factor, if we can. Factor is 32. That when I add the two numbers, I get 12. What, 8 and 4? Like I need an x in there. X factor. So you get x equal to negative 8, x equal to negative 4. Now, does both of those numbers work? We check. And that's what I mean by the big Y. Check x equal to negative 8. So I go back and plug in to the original problem, log base 3 of negative 8 plus 7 plus log base 3 of negative 8 plus 5. This is log base 3 of negative 1 plus log base 3 of negative 3. And you plug that into your calculator and you get does not exist. Because I cannot take the log of a negative. Because these terms here must be positive. That's based on the definition for the domain, right? So we discard. X equal to negative 8. Check. X equal to negative 4. It works. Get log base 3. My space is running out, so I'm just going to plug in x equal negative 4. So that's negative 4 plus 7. This is log of 3 plus plug in there log of negative 4 plus 5. I get the log base 3 of 1. Okay, so and these numbers are positive, so we're good. And we know that log base 3 of 3 is 1, and the log base 3 of 1 is 0. So you get 1. you get the answer. All right, last one, dealing with mathematical modeling of logarithmic and exponential equations. Here, prehistoric cave paintings were discovered in a cave in France. The plant contained 14% of the original carbon-14. Used the exponential decay model. Why is it decaying? Because it's negative. All right. To estimate the age of the painting. Now it tells us that that we have 14% of the original. So the original amount is given by A naught. Thus, 14% of the original is A equal to 0.14 times A naught. So we're going to replace this A with 0.14 times A naught. So we have 0.14 times A naught is equal to A naught times e to the negative 0.000121 times t. Divide both sides by the A naught, so we get 0.14 is equal to e to the negative 0.000121 t. Since we have exponential form, we take the natural log of both sides. Natural log of 0.14 is equal to the natural log of e to the negative 0.000121 t. And so here we have the natural log of 0.14 is equal to negative 0.000121 t. And that's times, this natural log of e is just 1. And so what we end up with is the natural log of 0.14 is equal to negative 0.000121 t. And so t is equal to this natural log of 0.14 all over this negative 0.000121. And so you do that on your calculator and you get something like 16249. It's like 16248, point something, a little bit over 5. So we just round that off there. And it says years. It's interesting. Is that believable? I mean, who knows who was around, who was there? Well, I know I wasn't. I don't think not too many other folk were either. So, but that's that.